Hello mathematicians, we're now going to revisit simple harmonic motion, but this time we're going to be looking at the differential equation, which essentially means that we're going to work with equations which are functions of displacement. So simple harmonic motion, we know, can be defined as motion in which acceleration is proportional to displacement. We mentioned that when we were doing the time equations. It's also oppositely directed, which means that in equation form we have this. So the acceleration is proportional to displacement, so minus n, or n squared is the constant of proportionality. The negative in here means that the acceleration is always directed back towards equilibrium. If we have the motion centered about some other point than the origin, such as x0, then this equation can be written in this form. So if we're asked to find where the centre of motion is, for a case where it's not the origin, shuffle it into this form and read off the value of x0. This particular equation, or both of these equations, are what's known as second order differential equations. So the differential equations, because they have a derivative in there, and it's the second derivative with respect to time of displacement, so it's a second order differential equation. And we can solve these by the method of separation of variables. So if we have the fact that acceleration is d dx of a half v squared, which we've encountered previously, then that means that d dx of a half v squared actually equals minus n squared x from what we discovered above. And when we look at this equation here, then we can integrate both sides of this equation, and I'm going to actually put the limits into the equation. You don't have to do this. You could redo the calculations with finding the constant, and I might actually do that in a moment. But this is a shortcut. For extension 2 students, this is probably how we should be thinking of it. For extension 1, we're allowed to use this technique. And this technique means that we are going to go from some initial condition when v equals 0, and that would happen when the amplitude equals, or when the displacement, equals a, and then the particle is going to move to a point where its velocity is v and its amplitude is going to be 0. Its displacement is going to be 0. So when we do this, we're going to get that v squared equals n squared outside a squared minus x squared. Now I'll just do over here the longer version for you, and probably realistically this is the version that most of you would prefer. So if we go from this line here, d dx of a half v squared equals minus n squared x, I'm going to then say that we will take the integral with respect to x of both sides, so d dx of a half v squared dx, and that will equal the integral of minus n squared x dx. So the integral of the differential cancels out, and we're just left with a half v squared, and the integral of minus n squared x becomes minus n squared x squared on 2, and we have plus c, our constant. So if we take one situation, which is when x equals a, v equals 0, then what that will give us is that 0 equals minus n squared a squared on 2 plus c, so c is n squared a squared on 2. So from that we get that a half v squared equals n squared a squared on 2 minus n squared x squared on 2. Obviously we can cancel that 2 out right across the equation, and we can then say v squared equals n squared outside of a squared minus x squared, and that's where we were before. Okay, occasionally you'll see it written as v equals plus or minus n outside of square root of a squared minus x squared, but this form is probably the most direct to use. So for this question here, a particle's motion satisfies this equation, which is an equation for velocity in terms of displacement. First part says show that the motion is simple harmonic and find these characteristics of the simple harmonic motion. So in that case here, we start with our equation for velocity. We use the fact that acceleration is the differential of a half v squared. So that becomes the differential of v squared on 2. And when we do that differentiation, we get minus 2x on 2. So therefore acceleration is minus x plus 7 on 2. And we can see that what this is the layout where we have simple harmonic motion, which gives us acceleration is proportional to the displacement, it's directed back towards equilibrium, and it's centered about somewhere other than the origin because it has this 7 on 2 being added to it. So we could rewrite that as minus outside of x minus 7 on 2, but it's probably not worth doing at this point. We can then see that n squared, the number in front of x, is going to equal 1, so n equals 1. We only take the positive case because it's angular velocity. We just want the magnitude of that. And that's because we want to get the period, t equals 2 pi on n, which is 2 pi on 1, so we get 2 pi seconds. It makes no sense to talk about a negative displacement. Sorry about that. Now we also notice that the centre of motion is at 7 on 2. Now we then had to find where the particle is when its speed is half the maximum speed. So the x has its maximum value when v equals 0. Hang on, I haven't answered. Sorry, phone call messed things up. So find the centre and the period, we've done that, and the amplitude of the motion. So x is a maximum, so in other words x equals the amplitude when the velocity is 0. So if we look at our equation for velocity just here, when that will be 0 is at x equals 3 and x equals 4. So they're the two extremes of the motion. So this particle is oscillating between 3 and 4, and its centre is halfway between those at 3.5, obviously, and therefore the amplitude is 0.5. Now for the second part, find where the particle is when its speed is half the maximum speed. We know that the maximum speed occurs when the acceleration is 0, so that happens when x is equal to 7 on 2, so as it passes through the equilibrium position. And when that's the case, then the velocity, and that's plus or minus the square root of our expression for v when we put 7 on 2 into it, that becomes plus or minus a half. When it's talking about speed though, remember, we don't worry about the direction of the velocity. So we're just saying that the maximum speed is a half, and we want to find where the particle is when its speed is half that maximum, which is when its speed is a quarter. Again, we strictly speaking don't need to worry about that. So if we go to our equation and we put v squared as a quarter squared, which is 1/16, equals that, rearrange that equation, solve it via the quadratic formula because it's not a nice one with factors, and we get 3.5 plus or minus root 3 on 4 is the position at which the speed is half the maximum. Again, we feel good about that because it's obviously offset from the centre of motion, which was 7 on 2, or 3.5. So, what's the big idea in this section? Well, I think our definition of simple harmonic motion in terms of displacement is a big idea, and tying it in with the material that we know already, and beyond that, just being familiar with the maths of doing our work with regard to the correct variable. So if you then have a go at the odds in 3F, and Extension 2 students should probably have a go at question 20.